Decaf-Math ASMR, and a warm welcome if you happen to be new here. Today I wanted to do this extra sleepy video. At least I hope it's extra sleepy. I hope my videos in general are relaxing and a nice way to review. But sometimes I like to do extra sleepy and tedious type videos. And I thought that this was the perfect topic because the Euclidean algorithm for finding the greatest common divisor has this lovely pattern. It's repetitive and it has quite a nice flow. So I thought that it would be fun to just work through. So, of course, I can't help myself. I have to do a little bit of explaining. But once we understand how the algorithm goes, it's quite fun to just do the little calculations. So I encourage you to just relax and zone out if you want to. Just get your mind off of the everyday for a little bit. So remember that the greatest common divisor, the GCD, is the largest number that goes into the two numbers that you're looking for the GCD of. So in general, a divisor is a number that goes into another number. The greatest common one is the largest one that goes into both. So the Euclidean algorithm allows us to methodically figure out what that is without the prime factorizations, which we've talked about on this channel. So instead it just kind of runs line by line rather than factoring. So the main kind of idea is if I want to find the GCD of two numbers, let's just call them A and B, but we'll run specific numbers in a little bit. If I can write A in this form in terms of the other number B, B is the smaller number, by the way, B, Q plus R, where Q is the quotient and R is the remainder, which just basically means if I divide A by B, then I have that this GCD of A and B is equal to the GCD of B and this remainder. This is a remainder. So Q is just how many times A goes into B. These are just arbitrary placeholders, but those are the typical letters. So this is a result from number theory. We won't prove it today, but the idea here is we can use this fact and keep dividing A and B. So let me show you what that means. So let's say we do the GCD of 4, 5, 9, 6. 4, 5, 9, 6, and 884. Just random numbers here. So we have the larger one is this. This is A. This is B. So the first step is to take A, 4, 5, 9, 6, and then equal, and we want to find Q and R. So we do 884 for B, and now we want to figure out what blank and then plus blank is. And what we mean by quotient is when you divide this by this. So you can do this by, long division if you want to, like this. You can kind of estimate if you want to. You just want to find the biggest number where this times that does not exceed 4, 5, 9, 6 like you would if you were to try to divide this. So you can kind of guess and check. You might notice this is almost 9,000, and if you round up 1 and you round down 1, so this is 45, you could guess about 5. And you could try that out. I'm not going to do that though. I'm just going to go ahead and use my calculator. So I would do 4, 5, 9, 6 divided by 8, 8, 4. And I get 5.199. Can you see that? 5.199. So that means, rounding down because you want the largest but not exceeding. So you would do 5. And then to know what the remainder is, if you were to carry this out, you would multiply this out. But you can do 884. 884 times 5 is 4420. And then the remainder would be 4596 minus this. And I'm going to go ahead and just subtract 4596. Now I'm going to get a negative, and that, that difference is going to be the positive, the absolute value. So 176. So basically, if I were to divide this longhand, I would do 5 times 4 is 20. 5 times 8 is 40, 42. 5 times 8 is 40, 44. Minus 6, 7, 1. And that's how I get the 176. So if you recall from long division, in general, you can write this number as a product of this times this, this times this, plus a remainder if you have one. So here we are, we calculated Q and R, so the quotient and the remainder. Okay, so then what the algorithm then tells us, this is still A and this is still B. So what the algorithm tells us, or what this formula tells us, is that the GCD of A and B is the same as the GCD of B and R. So that means I can keep moving this, sliding it over. So I'm going to borrow this B and this R, and I'm going to write B as, let's say, B equals R times another quotient, a different Q or K or whatever other letter, plus L. Keep tracing this. So then you can say 884 equals, and then you move 176 in place of the B, and the B goes to A. So you do 176 shifting it over because you know that the GCD of these values is the same as the GCD of the A and the B. So I carry this again. Again, I can do the long division. Notice that this time it's significantly smaller. So again, 884 divided by 176. Right. So I notice then I have a 5. Again, you round down. And then, you can calculate this out. So you get 30, 35, 38, 880. So you have a remainder of 4. So now you calculated the next quotient and the next remainder. So then now I have a new thing and a new remainder. So we slide this over and slide this over again. So then we say 176 equals 4 times blah plus blah. And so we divide again, and notice that each time we divide, it just gets smaller and smaller, right? These numbers get easier and easier to work with, which is the whole point of this algorithm. I get 176 equals 4 times 44. And there's no remainder. There's no decimal, so that means the remainder is 0. So the GCD of 4596 and 884 is the same as the GCD of 884 and 176, which is the same as the GCD of 176 and 4. So what the algorithm says now is once we get a remainder of 0, the answer, the actual GCD of your original, 2 numbers here, is the remainder of the line before it. So now that I hit 0, I look up a line, which is this one, and the remainder was 4. So that means that the GCD of 4596 and 884, assuming that we didn't make any calculation errors, is 4. So I think it's super cool. It has a nice kind of shift and flow and shift and flow. The key thing to keep in mind is that this is the form you're looking for. So the larger number equals the smaller times something plus something, and it's our job to figure out what Q and R. Q is the largest number of times this goes into without being bigger. So you would never put a 6 here and this would never be negative. And it has to be the largest number of possible times. And then R is going to be a remainder. And so then we take the smaller number, the second number, and then set that equal to R times another number plus another number. And you keep shifting it over until you get down to a 0. And this might take only a couple steps, or it might be very, very long, but you can imagine the computer running this very quickly. Once you get a remainder of 0, you look at this step before it, and your GCD is the R, the last R. So in this case, 4. So thought that this was really cool, but let's do one where we have a really large number, just out of curiosity. And so let's find the GCD of 1, 2, 3, 4, 5, 6, 7, 8, 9, and or maybe have confusing, but not too many, so that there's only like, 2 steps. So imagine if we tried to do the prime factorization method for this. That might take forever trying to factor this. Just keep dividing out 2's or 4's or whatever. Or 2 and 2 squared or 8 or whatever. But instead we're going to run this algorithm. So remember, our general form is A is B times some number plus some number R. We're just going to do the shifty pattern. So we're going to start with 1, 2, 3, 4, 5, 6, 7, 8 equals 9, 8, 7, 6 times something plus whatever the remainder is. So in this case, I'm going to most definitely use my calculator. 1, 2, 3, 4, 5, 6, 7, 8 divided by 1, 2, 3, 4, 5, 6, 7, 8 divided by 9, 8, 7, 6. So it's 1, 2, 5, 0. And we round down, even though there's more stuff. 1, 2, 5, 0. And then I'm gonna go ahead and do this times this. 9, 8, 7, 6 times 1, 2, 5, 0. That's what we would actually get. So I want to know what the remainder would be. So 1, 2, 3, 4, 5, 6, 7, 8 minus my previous answer to know what the difference is. So that's 678. Nice. So now this is my R. This is my B. So we're shifting the B. So I know at first it can be kind of tricky if you're looking at it for the first time. It's not Q that gets shifted, it's the B that shifts. So we now move B over 9, 8, 7, 6 equals R. So those are the two numbers that we carry over. 6, 7, 8 times something plus something. And we do the same division again. So now 9, 8, 7, 6 divided by 678 is 14.566. Rounding down to know the largest number of full times. And then we multiply this. So 6, 7, 8 times 1, 4 is 9492. And then I want to know what the remainder would be. So 9876 minus 9492 is 384. So that's the new remainder. And again, this is our B. That's what we're working with, not the quotient itself. So we slide it over. And notice how nicely the numbers are becoming more manageable, right? So times something plus something. And this one I can look at and see one time, but we can use our calculator. 678 divided by 384. 1.765. But we're rounding down again. And so 384 times 1 is 384. But to know the remainder, it's 294. So that's our R. So we just keep on going. We keep on sliding over. This is our B. We slide it over. Like this waterfall. I love it so much. 384. It's just a fun little algorithm in number theory. And a lot of times, we go over the proof too, I think. But, let's see, Q. In intro number theory class. one more. And then 384 minus 294 is 90. And at any point, if you can recognize the GCD, you can just stop. But for the sake of the algorithm, we're just going to keep flowing. So like at this point, you could use a different method if you wanted to, but this is way more fun. So this is R and this is B, so we slide it over, slide it over. So we have 294 equals 90 times something plus something. So in this case, 294, 90. So that'll be, I think, 3. But let's do it. 294 divided by 90. 3.26667. So we're going to round down to 3, leaving us with 270. So the remainder will be 24. And then we just keep on going. We keep on going. So at this point, this is B and this is R. So you might be able to kind of eyeball this and kind of tell what the GCD is between 90 and 24. But we can keep doing our slide down. So 90 equals 24 times what plus what? So 90 divided by 24. We round down, so that'll be 3. 24 times 3 is 72. The difference between 90 and 72 is 18. We just keep on going. This is R, and this is our B. So we slide and slide. And the reason why I'm carrying out every step like this is to really show that eventually this does terminate and we do get a 0, because the algorithm kind of depends on hitting a 0 so we can look up. So that's kind of important, and that's actually part of the proof, is that it actually indeed terminates. So 18 goes into 24 once. That's 18. So, and then 24 minus 18 is 6. So, nice. And now we have, this is our B, this is our R, and I think this is our final slide. So 18 equals 6 times what plus what? It's 3 indeed. So that's our remainder of 0. So now that we've hit a remainder of 0, we look up one step, and this R is our greatest common divisor of our original numbers, and coincidentally but not every pair that we've come up with here. So the GCD of 9876 and 678 is 6, but our original question is the GCD of 1, 2, 3, 4, 5, 6, 7, 8, and 9876, assuming we don't have any calculation issues, is 6. And the GCD of 9876 and 678, and the GCD of 678 and 384, and the GCD of 384 and 294, and the GCD of 294 and 90, and the GCD of 90 and 24, and the GCD of 24 and 18, and the GCD of 18 and 6 are all 6. Isn't that cool? I love this pattern. Just flow. It's just nice. You can take this step by step. Like we said, a calculator could do this much quicker, or not calculator, a computer could run this algorithm much quicker. But that's the main thing. So we can do the proof sometime. I'll have to review too, but one piece is most definitely needing to show that it terminates at some point. And then I believe another piece of that proof would include some properties of how like a number divides something. So, what it means to be a greatest common divisor. So you'd probably have to show that there's a divisor, and then to actually show that it's indeed the greatest common one. But we'll do that another time. I think you have to use some properties of divisibility. So it's been a while, but I do hope that this rundown of the actual algorithm is interesting or sleepy. I just thought that this pattern would make for good tingles and relaxation. I think it's really satisfying. And I'll definitely have to go back and check that we actually got the correct numbers. But all in all, I hope that you rest well, sleep well. Sweet dreams. I hope that this offered you a little bit of peace during this time. Thank you for hanging out with me, and I'm sending you my love and prayers. And as always, if you need any specific prayers or would like any love or support, let me know in the comments, and I will see you around.